Okay, so this is part 2 of the video. Hopefully you stopped it at 15:10 like I asked you to, so that I could re-explain this one better. I did not like the explanation from before. So this is the 5th example again. In this problem it says the 4th term of a geometric sequence, so again geometric sequence, is 125, and the 10th term is 125 divided by 64. And the question is find the 14th term and assume that the terms of the sequence are positive. So terms are positive, and we'll talk about what that means here in a second. So what we're going to do is write down what we know. I know that a sub 4 is 125, and I know that a sub 10 is 125 over 64. So what I want to do is I want to find the ratio of these two. Now these are non-consecutive, so this is an important example of a non-consecutive. But we'll be able to use that ratio to find the common ratio between consecutive. So I will divide these two. So I'll do a10 divided by a sub 4. That is 125 over 64 divided by 125. And you can do this in your calculator, but we want to try to keep as exact as possible. So this 125 is over 1. Instead of dividing fractions, we multiply by reciprocals. So that's 125 over 64 times 1 over 125. And the 125s will cancel, and this is 1 over 64. Now, what does this represent? Well, we have to look at these two terms and say how many terms are between them. Between 4 and 10, there are 6 terms. So 6 terms between. So what that means is this 1 over 64 is r to the 6th power. So what that means? R to the 6th equals 1 over 64. So again, think about it. If I go from the 4th term to the 10th term, what I'm doing is I'm taking the 4th term and multiplying it by the common ratio r. And then I'm taking the 5th term and multiplying it by r. And the 6th term times r. And the 7th term times r. So I'm multiplying by r 6 times to get from the 4th term to the 10th term. R times r times r 6 times is r to the 6th. Okay? So now to find r, we need to take the 6th root of this. Now, what's going to happen is we do get r, and now here's where this comes into play. This assume that the terms of the sequence are positive. When you take a 6th root, you get 2 answers because it's an even root, plus or minus. So you would do plus or minus, and now you can type this in the calculator or recognize that this is just the 6th root of 1 over, and 64 is 2 to the 6th. Okay? So maybe you could recognize that. But this right here means that since the terms of the sequence are positive, we don't worry about the negative, we just keep the positive. Okay? And that'll simplify to an r value of 1/2. 6th root of 1 is 1. 1 to any power is still 1. 6th root of 2 to the 6 is 2. Okay? Alright, so I found r. Now, I want to find the nth term. So now, I want to find, a sub n. A sub n is a sub 1 times r to the n minus 1. That's the general form. Now, I know what r is. R is 1/2. But I do not know what a sub 1 is. I need to find that. Well, we can do that by using either a sub 4 or a sub 10. We can plug that in for a sub n down here. So let's use a sub 4 because it's not a fraction. So a sub 4 equals a sub 1. R is 1/2 to the 4 minus 1. A sub 4 is 125. 125 is a sub 1, and now this is 1/2 to the 3rd. And 1/2 to the 3rd means 1 to the 3rd, which is 1, and 2 to the 3rd, which is 8. That's 1/8. And now to find a sub 1, just times both sides by 8. And 8 times 125 is 1,000. And now we can plug the 1,000 in for a sub 1. So now we can use this formula. A sub n equals 1,000 times 1/2 to the n minus 1. And now I want to find the 14th term. That's a sub 14. That's 1,000 times 1/2 to the 14th minus 1. And again, you may use your calculator. That's fine. So 1,000 parenthesis 1/2 to the 13th power. And you get a decimal of 0.122. And that's fine. I'm not going to be too picky. Or, if you use the 2 fraction button on your calculator, math, 2 fraction, it is a nice even 125 over 1064. Not a nice even, but a nice fraction like that. Oh, sorry, 1024, not 1064. 1024. Okay. So 125 over 1024. Good. So hopefully this is the first problem, or first time you've seen this problem, and you can go about doing this with future problems. Non-consecutive. All right. So now let's talk about sums. The sum of a finite geometric sequence. Okay, so we're going to talk about finite and infinite. Okay, so this is a finite sum. All right. Now this is the formula. Now from here, okay, this is the sigma notation, but we're just looking for this. The sum of n terms is the first term times this fraction, 1 minus r to the nth power over 1 minus r. Okay, so this is the formula that you should know. It'll be on the sideboard though for you. N is the number of terms. Number of terms. A sub 1 is the first term. And again, you cannot be wrapped up in the fact that it's always A sub 1 with 1. This could be A sub 0. This could be A sub 6. It's whatever that first number is. So again, whatever that first number is, that's the first term. And then R is the common ratio. And that should be given to you in the problem, in the sigma. Okay. We will skip the proof here. Sorry. Again, it is a clever proof, but we'll skip. So this is how we're going to find the sum of a finite geometric sequence. Alright, so let's see if we can put this into motion here. Okay, so let's find the sum here. So we are looking for the sum of n. A sub 1, the first term times this fraction, 1 minus r to the n over 1 minus r. Alright, and when I do this, okay, I need 3 things. I need the number of terms, I need the first term, and the r. So the number of terms, n equals, well, if I'm counting from 1 to 12, that's 12 terms. Next, the r. The r is the common ratio. That is the base of the exponent. The r is 0.3. And now I want to find the first term. And to find the first term, I'm going to plug 1 in for I. So that is 4 times 0.3 to the 1 minus 1. And 1 minus 1 gives you an exponent of 0, which makes the 0.3 go away, and your A sub 1 in this problem is 4. Alright. So I just plug these numbers in. So S sub 12. So the sum of the first 12 of this finite sequence is going to be 4 times 1 minus, now I'll put the 0.3 in its own parenthesis, to the nth power, 12, all over 1 minus 0.3. Now when you do this, you need to be very careful with parentheses. So when you input this, the numerator gets its own parenthesis, and the denominator gets its own parenthesis. So I'll speak it out loud, hopefully, as you do it in your calculator at your desk. So we have 4 parenthesis, and then parenthesis for the top. 1 minus parenthesis for the 0.3. Close the parenthesis, raise to the 12. Close the parenthesis for the top. divided by parenthesis 1 minus 0.3. Close the parenthesis for the bottom, close the parenthesis for the entire thing. And we get a sum of 5.714. Okay. So there we go. So there's the sum of a finite geometric sequence. Okay. All right, now, the book has this discussion of how your sequence should look. They really want you to keep in mind that the exponent should be I minus 1 for this to follow this idea here, okay, of, number of terms, this a sub 1 being that number right there, and then the common ratio, okay? But the way that I explained it, if you just remember that that first term is what you get when you plug in that lower limit, then you don't need to worry about this, okay? So, again, just remember that that first number on the bottom of sigma is what goes in for the I to find the first term. So you'll see they have this problem right here. I'm going to rewrite it right here, okay? No, I'm not. It's right there. Okay. So we need to find this sum. Now this is very similar. The only difference is the exponent, right? Pay attention to that exponent, right? It's not I minus 1, it's just I. Well, let's see how this affects the problem, okay? Well, I want to find the sum of the first n terms. So I have the first term times 1 minus r to the n over 1 minus r. So I need to know n, a sub 1, and r. So I'll do that over here. So what is n? Well, n is the number of terms. I'm still counting from 1 to 12. That's 12 terms. R is still that common ratio of 0.3. But now to find a sub 1, I plug 1 in for the exponent. 4 times 0.3 to the first. So again, this 1 goes in that exponent. And notice the exponent doesn't become a 0, it's a 1. So that first term is 4 times 0.3. The first term is now 1.2. So see the difference. See how it changes that first term. So when I find the sum now, the first term is now 1.2. And then this fraction is still the same, 1 minus 0.3 to the 12 over 1 minus 0.3. And again, be very careful with your parentheses. Maybe you can try it on your own. 1.2, parenthesis, and I'll just do it silently, and hopefully you get the same thing. So I get a sum now of 1.714. So just be very careful, right? Just be very careful of that exponent. And again, if you're looking for a geometric sum, make sure you get the number of terms right, and just plug in the first number on the bottom of sigma to find your first term value. Okay. Now, let's talk about the sum of an infinite geometric series. And to begin this, I need to point out this right here. For the geometric series to have a sum, your r value must be less than 1. And again, we ignore the negative. So ignore the negative, the r value must be less than 1. Here is the reason why, okay? When you think of geometric series, you need to think of exponentials. Right? So we think of exponentials. Well, let's take a look at what a graph looks like for an exponential, right? Y equals a b to the x. Right? If that b is less than 1, here is what the graph looks like. And there was an asymptote. Okay? So that is if b is less than 1. So again, we got to think of this base as r. So now notice, as this goes to infinity, and again, this is the x-axis or the n-axis. As that goes to infinity, look at what happens to your graph. This is approaching 0. Approaches 0. Right? It's going towards the x-axis, so its y value is getting smaller, 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 all the way to 0, not touching it. That is why this becomes a 0. That explanation right there. The fact that as you go towards infinity, as this n value goes towards infinity, if r is less than 1, then it follows this graphic behavior. And it goes close to 0, so we just eliminate it. So the numerator now just becomes a 1, and we bounce this a sub 1 to the top. And that's how this formula comes to be. Okay? So again, hopefully that explanation helps a little bit to understand why that r to the n goes away. Now, if your r is bigger than 1, then you'll see it does not have a sum. And here is the reason why. If r is bigger than 1, then when you graph it, it is a growth graph. And as x or n goes to infinity, look what happens to your graph. Your graph is going up. This is going to, not approaching, it's going to infinity. And it has no sum. Okay? So this is the reason why, if your r is greater than 1, you cannot find this infinite sum. So make sure, double check, r is less than 1. All right? And use this formula. Okay, so let's try to find a couple infinite sums here. All right. So find each sum. And you'll see this infinity sign means infinite. So I'll just circle it. So the first thing we do is we should check the r value. R equals, it's the number what the exponent is raised to. R equals 0.6, which is less than 1. So we can have an infinite sum here. So we need to find the sum, which is equal to a sub 1 over 1 minus r. I need these two things. So r is, of course, 0.6. What is a sub 1? Well, again, plug in 1, the bottom number for the exponent. 4 times 0.6 to the 1 minus 1. The exponent becomes 0, that base goes away, and our a sub 1 is 4. So this sum is 4 over 1 minus 0.6. When you do this in the calculator, you could subtract the bottom first, or you can use parentheses. 4 divided by parenthesis, 1 minus 0.6. And this is 10. All right. So again, as you go towards infinity, as you keep adding up these terms, this sum approaches 10. Okay? All right. B now. So B gives us a list of numbers. So it gives us, this is a sub 1, that's a sub 2. So we need to find the common ratio first. So the common ratio is going to be a sub 2 divided by a sub 1. And I could have used any consecutive terms here. 0.3 divided by 3. And when you do 0.3 divided by 3, you get 0.1. So you can use that, or you can use the fraction 1/10. We're going to use 0.1. All right. So when I build my formula, okay, the first term is going to be 3. So I'm going to build my formula just like the standard they give me. So sigma from I equals 1 to infinity on a sub 1 r to the n minus 1. So that would be sigma from I equals 1 to infinity on 3 times 0.1 to the I. This should be an I, not an n, sorry. So I'm going to erase this n here, make it an I. To the I minus 1. So again, because I was given 3 as my a sub 1, I know what my a sub 1 is. I don't need to plug it in. So when I find this sum, I am going to use 3 as my a sub 1, and I found my r, which is 0.1. So this sum is 3 over 1 minus 0.1. It's 3 divided by parenthesis 1 minus 0.1. And I get something like 3.3 repeated. If you go to fraction, it's also 10/3. So that is what this sum is approaching. And again, maybe you could have saw that by adding up these terms, right? 3.3, 3.33, but I want you to find the sigma notation because you might have to do that, and then plug in the sum formula. So this is infinite sums. Okay, last one here. We're going to talk about an increasing annuity. Okay, an increasing annuity. And before we begin, this is going to be very similar to compound interest. Similar to compound interest. Okay. Now the only difference is right here. It says a deposit of $50 is made on the first day of each month. So when you do compound interest, you put money away and you never touch it, and it just grows interest. Well, now we're going to continue to give money towards this annuity, okay, every month. So that's an important idea. All right. So it says a deposit of $50 is made on the first day of each month in a savings account that pays 6% compounded monthly. What is the balance at the end of 2 years? We started off like compound interest. The formula, because it says monthly, we have to use this formula. Maybe you remember. So this says A equals P, parenthesis 1 plus R over N to the NT. So what do we have? Well, this is A is the amount, that's what we're trying to find. P is what you deposit. So P is 50. R is the rate, that's 6%, now as a decimal though, and the N is this word monthly. That's how often you do it. And the time is, of course, 2 years. Alright. So when you plug these numbers in, A equals 50 times 1 plus 0.06 over 12, raised to the 12 times 2 power. I want to simplify what's inside here. So A equals 50, 1 plus parenthesis 0.06 divided by 12. So that's 1.005, and then 12 times 2 is 24. So if I wanted to find the compound interest just by depositing $50 and letting it sit there, this would be the answer. This would be compound interest. But this is not what I want. I want to do the annuity problem, which means that I am continuing to invest money. So this is a sum problem. So we sum from I equals 1, first month to the 24th month, of our initial deposit, 50, times the 1.005, and now the exponent represents the month, and the month is just going to be I. We're going to plug 1 in, we're going to plug 2 in, 3 in, 4 in. This will give us the sum of the 24 months. All right? Now this is a finite sum. Sorry about that message. This is a finite sum. So we're going to use the formula S sub n equals A sub 1, R 1 minus R to the nth over 1 minus R. And I need those three numbers. Okay? So I'm going to do it in red right here. So n is the number of terms. I equals 1 to 24. 24 months. In your 2-year span. AR is what your common ratio is. 1.005. And then A sub 1 is how much you start with in the first month. So in the first month, you put the 50 away, but then you get the interest accrued. So plug 1 in for I. So that's going to be 50 times 1.005. That's $50.25. So now I can plug away. And I'll do it right here. A sub 24 equals 50.25 times 1 minus 1.005 to the 24 over 1 minus 1.005. And I'll put the answer right here. So, when you do 50.25, remember your parentheses. I got a number rounded to money, 1277.96. Okay? And again, that's how much money you would accrue over the 24 months if you put $50 in each month. All right? So again, a little bit different to compound interest. Okay, so then your homework over the weekend is to complete this homework. And we will talk all about it on Tuesday, as well as review. All right, thanks for watching. We'll see you on Tuesday.